Now we get to practice drawing some triacylglycerols or triacylglycerides from descriptions of the molecule. And if you're printing these worksheets out, I've left you tons and tons of space to draw these so we can draw them nice and big. So for all triacylglycerols, when you're asked to draw them, they're all going to have that glycerol backbone. And I always like to start with the glycerol backbone. The top and the bottom carbon will each have 2 hydrogens, and the carbon in the middle will have 1. So they'll all have that same general structure. And then over from the carbon, we're going to have a single bond to the oxygen, and this is where we transition from the glycerol to the fatty acids. And the next thing that we have is the carbon-oxygen double bond. And this order is really important. So don't think, oh, you can just mix and match. Like, it's really important that you are starting with the carbon and then going to a single bond oxygen and then to the carbon-oxygen double bond. That's the way that it is in nature, and that's the way that you need to draw it. So from here on out, now we are going to have our fatty acid chains that are on this triacylglycerol. So now is where we need to stop drawing and pay attention to the problem and see what it's asking us to do. It says we're making this triacylglycerol from lauric acid and myristic acid. And then it's also describing what lauric and myristic acid look like, so we don't have to look the structures up, which is nice. Lauric acid is saturated, which means that it only has carbon-carbon single bonds, all carbon-carbon single bonds, and there's 12 carbon atoms. And myristic acid is also saturated, so it also has only carbon-carbon single bonds, and this one has 14 carbon atoms. So we're ready to draw these. It doesn't tell us where on this we should put the lauric or myristic acid, which means we can put it wherever we want. It also doesn't tell us how many we need to have. We need to have a total of 3, but 2 of them are going to be lauric acid and 1 myristic, or 1 lauric and 2 myristic. But we don't have any rules here, which means we can kind of just do whatever we want to do. So I am going to, one time, let's do the first one, make the first one lauric acid. 12 carbon atoms, and this counts as one of them because that is the first carbon of the fatty acid. So then here's number 2, number 3, number 4, 5, 6, 7, 8, 9, 10, 11, 12. What a pain. And now I've got to fill hydrogens in on all of these carbons. So again, this isn't cool. And like I said, I'm only going to do this one time. I don't want to have to do this again. For the rest of my fatty acid tails, I'm going to draw line structure. So I'm mixing and matching. In this particular drawing, I'm mixing and matching. I've got some condensed notation up here. I've got some full-on Lewis notation out here. And now I'm going to do some line structure. So for my next one, in the next position, I'm going to draw lauric acid again. And again, that's going to be my carbon number 1 in my line structure. Here's carbon number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there they are. And then in my last one, now I have to put a myristic acid in place there. I don't know why I wrote a number 2. So here, this one is going to be a myristic acid with 14 carbon atoms. I've got carbon number 1 right there. Here's carbon number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There it is. See, that's not so bad. Let's see what is on the next question. Draw the structure of another triacylglycerol formed from glycerol. So first thing I'm going to do before I even finish reading this problem is I'm going to make my backbone for myself here. 2 hydrogens on the top and 2 hydrogens on the bottom and 1 hydrogen in the middle. Each carbon has a single bond to an oxygen, and this is the part where we transition from the glycerol to the fatty acid. So next thing over is the carbon-oxygen double bond. And for all of these, this is carbon number 1 of the fatty acid. So now let's take a look at what kind of fatty acids we're working with here. We have palmitoleic acid, and that is 16 carbon atoms, unsaturated at C9. That's carbon 9. So this one's going to be tricky. And stearic acid, saturated, 18 carbon atoms. So that one doesn't sound so bad. So let's do the palmitoleic acid first, get it over with. We already have 1 carbon. We need to draw 16 more. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I had to stop for a second because I realized I said we already have 1. We have to draw 16 more. 1 plus 16 is 17. We should only have 16. So I got to double check to make sure I did not make a mistake. Looks good. Okay. And so there's all 16 carbon atoms. And then now we have to pay attention to this part, unsaturated at C9. So where's C9? Here's C9. That is where unsaturated means that you have a carbon-carbon double bond. So C9 is where the carbon-carbon double bond starts. And it goes from C9 to C10. So there's our carbon-carbon double bond. And we're not going to pay any attention to if it's cis or trans. We're doing enough work right now as it is. So I'm going to actually delete these 2 guys to really highlight that double bond. So, okay, let's not do that one again. Let's do stearic acid 2 times. Stearic acid is saturated, so that means it only has carbon-carbon single bonds. All carbon-carbon single bonds with 18 carbon atoms, and we've already drawn 1 of the carbon atoms right here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You know, now I kind of feel like a wimp for saying I didn't want to draw palmitoleic acid 2 times. So you know what I'm going to do? I'm going to put palmitoleic acid down here at the end again. 16 carbons, unsaturated at C9. We're starting with carbon number 1. Here's 2, 3, 4, 5, 6, 7, 8, 9. I'm going to stop for a second because from 9 to 10 is my double bond. So now I'm at 10, 11, 12, 13, 14, 15, 16. And there that guy is. Let's take a look at what's next. So unlike fats and oils, cocoa butter, which is used to make chocolate, which is a triacylglycerol, is uniform in composition, meaning that there's not a lot of variety in the fatty acids that are put together in the cocoa butter molecule. All cocoa butter triacylglycerols contain oleic acid bonded to the secondary OH group, and then either palmitic or stearic acid bonded to the primary OH groups. Ooh, this sounds exciting. Draw the structures of 2 possible triacylglycerols. So we're going to do 2. So that means I need to make 2 glycerol backbones. Top and bottom carbon each have 2 hydrogens. The middle carbon has 1. Top and bottom each have 2. Middle carbon has 1. And the next thing is the oxygen. And then after that, the carbon-oxygen double bond for us to transition to the fatty acids. So we've got our framework ready for us to now pay attention to this problem. And the problem says oleic acid bonded to the secondary OH. What does that mean? It's been a while since we thought about secondary OH. So a secondary OH is an OH group that is bonded to a carbon that is bonded to 2 other carbons. An OH that is bonded to a carbon that's bonded to 2 other carbons. So this is our secondary site right there. And this is where we need to put the oleic acid. Now watch this laziness. Just in the interest of saving time, not needing to draw out massively long carbon chains, you're not, taking away any special skills by drawing 18 carbons in a row over and over again, or however many might be in oleic acid. We're just going to do it like that. So there's our oleic acids bonded to the secondary group. And then either palmitic or stearic acid bonded to the primary OH group. So let's remember what that means. So let's make a note here. This is our secondary OH. A primary OH is an OH that's attached to a carbon that's attached to only one other carbon. So this would be primary. And maybe that carbon is to the left, or maybe it's over to the right. It could be either one. So our primary carbons are these guys right here, a carbon that's bonded to only one other carbon. Carbon bonded to only one other carbon. And so at these sites, we can have either palmitic or stearic, our choice. So maybe my guy on the left, I'm going to give him 2 stearic acids. Let's try that. And again, this is just, I'm just choosing what I feel like choosing. I don't have a rule here that I'm needing to follow. This one, let's put palmitic on the top. I don't know if you can hear my rice maker is singing a song to me right now. Palmitic on the top, and we'll put stearic acid down here on the bottom. And there's many correct answers to this problem because you have a lot of options of how you could put this together. So that's just one way that we could do it. Last question asks, how many different triacylglycerols can we make from a total of 3 different fatty acids? Draw all possible structures using generic A, B, and C. So what I'm going to do to make this even easier is that I'm just going to go back to our rectangle skeleton representation of glycerol. And one option would be for us to put all A's on that glycerol. Another option would be for us to put all B's on the glycerol, or, as you can imagine, all C molecules. And this is an exercise that's really more fun to do when we're actually together in class because we can kind of make a little competition. Who can think of the most possible structures of all of these different combinations? There's a lot of them. There's a lot of different ways to put these together. And so, I'm not going to really go through every single possible option here because I feel like it's not necessarily the best use of time, but you get the idea. There are many of them, lots of different ways that we can put 3 different fatty acids, up to 3 different fatty acids on a triacylglycerol.